In episode 25, titled Picking a Topology, Mesh, Hub and Spoke, Point to Point, we treat topology choice as a balancing act between simplicity, resilience, and growth, because the shape of the network determines how traffic moves, how failures feel, and how painful future expansion becomes. The exam tends to present topology as an architectural decision hidden inside a scenario about branches, cloud connectivity, latency complaints, or availability requirements. When you choose a topology, you are implicitly choosing where control points live, where traffic concentrates, and which failures are survivable without heroic intervention. A topology that is perfect for a small, stable environment can become a constraint in a growing hybrid network, while a topology that is resilient at scale can be wasteful and hard to operate if the organization lacks maturity. The core skill is matching the topology to the story the prompt is telling rather than to your favorite diagram. The goal here is to make topology selection feel like a practical reasoning exercise you can repeat consistently. Before we continue, a quick note: this audio course is a companion to the CloudNetX books. The first book is about the exam and provides detailed information on how to pass it best. The second book is a Kindle-only ebook that contains 1,000 flashcards that can be used on your mobile device or Kindle. Check them both out at cyberauthor.me in the Bare Metal Study Guide series. A star topology centralizes switching, which makes it easy to understand and manage because everything connects through a central point. But it also increases core dependency risk because that center becomes a critical failure domain. In a star, spokes connect to a central switch or hub, and traffic often traverses the center even when two spokes are communicating with each other. The benefit is clarity, because the path is predictable and policy enforcement can often be concentrated at the core. The downside is that the core device, the core link, or the core power and cooling becomes single points of failure unless you build redundancy into the core itself. Even with redundancy, the core remains a concentration point for throughput and for operational impact, so misconfigurations and overloads can have wide blast radius. In exam scenarios, star topology is often implied when a campus or small site is described with a single central switching layer, and the correct answer depends on whether the scenario tolerates that core dependency. The key takeaway is that star simplifies edges but demands careful attention to the center. A mesh topology increases resilience because it provides multiple paths between nodes, reducing dependency on a single hub. But it also adds cost and routing complexity because many links must be built, managed, and secured. In a full mesh, every node connects to every other node, which maximizes path diversity but becomes expensive quickly as the number of nodes grows. Even partial mesh designs, which connect only some pairs directly, require careful planning of routing, traffic engineering, and consistent policy enforcement across multiple paths. The resilience benefit is real because failures can be bypassed, and east-west traffic can take more direct routes, reducing latency and avoiding hairpin paths. The operational downside is that more links mean more routing adjacencies, more monitoring points, more failure modes, and more chances for inconsistent firewall or access control rules to create confusing outages. In exam logic, mesh solutions are favored when the scenario emphasizes high availability and distributed connectivity needs, but they are penalized when operations are constrained and simplicity is the dominant requirement. The design goal is to use mesh where path diversity pays off, not where it creates needless sprawl. Hub and spoke is a common compromise because it simplifies management and concentrates connectivity, but it can create hairpin latency when spoke-to-spoke traffic must traverse the hub, even when a direct path would be shorter. In this topology, spokes connect to a central hub, and the hub often provides shared services, internet access, or connectivity to a cloud region, making it a natural control point for security inspection and routing policy. The benefit is consistent control and easier troubleshooting because most paths go through the hub, and adding a new spoke typically requires only one new connection to the hub rather than many connections to other spokes. The risk is that the hub becomes both a performance and availability choke point, and spoke-to-spoke communication can be inefficient if large volumes of east-west traffic are forced to hairpin through the hub. Hairpin latency is not just a performance issue. It can also increase egress costs and increase exposure to hub failures for traffic that could otherwise have stayed local. In exam scenarios, hub and spoke often appears in branch-to-cloud designs because it provides a predictable control plane, but the best answer depends on whether the scenario expects direct spoke-to-spoke services. The key is that hub and spoke is controlled and scalable, but it trades directness for manageability. Point-to-point topology fits dedicated links because it is simple and direct, but it scales poorly because each new connection requires a new link, and link count can explode as needs expand. A point-to-point link connects two locations or two devices with a single dedicated path, which makes behavior easy to predict and often provides stable performance when the link is sized appropriately. This topology is common for specific use cases such as a dedicated branch uplink, a replication link between two data centers, or a private connection to a cloud region attachment point. The limitation is that point-to-point does not inherently provide a scalable fabric because it does not create a shared transit layer, and adding new sites means adding more separate links and separate routing considerations. Operationally, many point-to-point links can create a patchwork of exceptions that is hard to document and harder to keep consistent. In exam terms, point-to-point is a good answer when the scenario describes a small number of dedicated connections with clear purpose, but it is usually a poor answer when the scenario describes ongoing growth and many-to-many connectivity needs. The design lesson is to use point-to-point for deliberate, dedicated paths, not as a general growth strategy. A practical selection rule is to choose topology based on traffic patterns and failure tolerance, because those two factors determine whether you need direct paths, redundant paths, or centralized control. If most traffic is north-south, such as users accessing centralized services or branches accessing a central cloud region, hub-based models can be efficient because the hub is naturally in the path anyway. If most traffic is east-west, such as service-to-service communication across multiple sites or regions, more direct connectivity through partial mesh can reduce latency and reduce load on central hubs. Failure tolerance determines how much dependency on a single hub is acceptable, and whether you need alternate paths to maintain operations when a hub link fails. This is why exam scenarios often include clues like critical operations cannot tolerate downtime or latency-sensitive transactions time out, which are signals that topology must support resilience and performance simultaneously. Cost and operational constraints then shape how far you can push resilience, because not every environment can afford full mesh or the staff to operate it safely. The best answer is the topology that matches the dominant traffic pattern and meets failure tolerance with manageable operational complexity. Consider a scenario connecting branches to a cloud region using a hub, because this is a very common hybrid pattern and the exam often expects you to recognize its benefits and its risks. In this scenario, each branch connects to a central hub that has a strong connection to the cloud region, and the hub provides consistent security inspection, routing control, and centralized management. This can reduce the number of cloud attachments needed and can simplify policy, because the cloud sees a smaller number of trusted connectivity points. It also simplifies onboarding new branches because each new branch needs only a hub connection rather than multiple peerings. The risk is that the hub becomes a critical dependency, so resilience must be built into hub links, hub devices, and hub power and operations, or the entire branch population can be impacted by one failure. If branches also need to talk directly to each other for local collaboration or voice, the hub can introduce hairpin latency that degrades experience. In exam reasoning, hub and spoke is often the best fit when the traffic is primarily branch to cloud and when centralized control is valued, as long as the design includes hub resilience appropriate to the availability requirement. Now consider a scenario requiring east-west service connectivity that favors partial mesh, such as multiple sites hosting services that call each other frequently and where latency matters. In this scenario, forcing all traffic through a hub can create unnecessary delay and can overload the hub's links, especially if service-to-service calls are chatty or if data replication is heavy. A partial mesh can provide direct paths between the sites that exchange the most traffic, while still using a hub for less common paths or for centralized services and inspection. This approach provides resilience and performance where it matters most without the cost and complexity of full mesh everywhere. The design challenge is to keep routing and security policy consistent because multiple paths increase the chance of asymmetric routing and policy drift if controls are not standardized. Exam scenarios that mention timeouts, east-west heavy patterns, or distributed microservices often signal that direct connectivity is valuable, making partial mesh a plausible best answer. The key is to mesh where the traffic justifies it while keeping the overall design understandable. A hidden single point of failure at the hub device is one of the most common topology pitfalls because organizations often add redundant links but forget the hub itself or its supporting dependencies. A hub can be redundant in concept but still fragile if it relies on one device, one firewall, one router, one power feed, or one misconfigured high availability pair that fails open or fails closed in unexpected ways. This failure domain is especially dangerous because hub failures are loud, affecting many spokes at once, and recovery often requires coordinated changes under pressure. The exam sometimes tests this by presenting a hub and spoke design and asking for the best improvement, where the correct answer is adding redundancy at the hub rather than adding more spoke links. It can also test it by offering an answer that assumes the hub is fine, while the scenario hints at strict availability requirements, making single hub designs inadequate. The lesson is that hub dependency is not inherently wrong, but it must be acknowledged and engineered for, because the hub is a concentration point for both traffic and risk. If you choose a hub, you must also choose a hub resilience strategy. Overmeshing is the opposite pitfall, where adding too many links creates operational burden and inconsistent policies, and the network becomes harder to predict than it is to break. Overmeshing often starts with good intentions, such as improving resilience and performance, but it can produce a topology where routing is complex, troubleshooting is slow, and security enforcement becomes inconsistent across multiple paths. Inconsistent policy is especially dangerous because traffic may take different routes depending on dynamic conditions. And if inspection and filtering differ by route, you can create blind spots or intermittent application failures. Overmeshing also increases configuration surface area, which increases the probability of errors and makes auditing more difficult. In exam scenarios, answers that propose full mesh everywhere often sound resilient, but they may be wrong when the scenario emphasizes limited staff, cost constraints, or a need for consistent inspection. The best answer in those cases is often a controlled partial mesh or hub and spoke with targeted direct links because it provides benefits without unmanageable complexity. The guiding idea is that resilience should be engineered, not improvised through link sprawl. There are a few practical quick wins that improve any topology, such as standardizing routing, documenting paths, and testing failover, because topology value is realized only when behavior is consistent under change. Standardizing routing means using consistent routing strategies and preference rules so traffic paths are predictable and so failover behavior matches expectations. Documenting paths matters because topology diagrams and route intent help teams troubleshoot without guesswork, especially in hybrid networks where multiple domains meet. Testing failover matters because untested resilience is not resilience, and many topology failures only reveal themselves when a link actually goes down and traffic shifts. These practices reduce the chance that a topology that looks good in design becomes a fragile system in production. They also help contain incidents because teams can recognize expected failover behavior and distinguish it from misrouting. In exam reasoning, answers that include validation and operational discipline often align with best answer logic because they acknowledge that networks must be operated, not just designed. The key is that good topology is not only a shape, it is a set of verified behaviors. A useful memory anchor is traffic, tolerance, cost, and operations choose topology, because these four factors are usually the deciding forces in scenario questions. Traffic reminds you to ask whether flows are mostly north-south to centralized services or east-west between distributed services, because that determines whether direct links are valuable. Tolerance reminds you to ask how much failure can be tolerated and how quickly recovery must occur, because that determines how much redundancy and path diversity you need. Cost reminds you that links and complexity have real price, and not every organization can afford full mesh or multiple high-capacity hubs. Operations reminds you to ask whether the team can manage the routing, security policy, and monitoring complexity that comes with the chosen shape, because unmanaged complexity becomes its own outage generator. When you can recite these four factors, you can justify a topology choice in plain language and align it to scenario cues. This anchor keeps you from choosing a topology because it looks elegant instead of because it fits the constraints. To end the core with a selection prompt, imagine constraints that include 3 branches, a need for consistent security inspection before reaching cloud services, moderate east-west collaboration between branches, and limited operations staff. A hub-and-spoke topology with a resilient hub can satisfy the inspection requirement and simplify management, because policy and monitoring can be concentrated at the hub while branches remain simple. If east-west collaboration is moderate but latency sensitive, adding targeted direct links between the 2 branches that collaborate most can create a partial mesh overlay on top of the hub model without exploding complexity. A star topology could also describe the branch-to-hub structure, but the key design point is not the label. It is ensuring the hub is not a hidden single point of failure and ensuring failover is tested. A full mesh would likely be excessive under limited operations capacity, while point-to-point links everywhere would scale poorly and increase management burden. The best answer is the one that meets inspection and manageability needs while addressing performance hotspots with minimal added complexity. This is the kind of constrained justification the exam expects when it asks you to pick a topology. In the conclusion of episode 25, titled Picking a Topology, Star, Mesh, Hub and Spoke, Point-to-Point, the selection logic is to match the network shape to traffic patterns, failure tolerance, cost constraints, and operational maturity. Star topology centralizes switching and simplifies edges, but increases dependency on the core, while mesh increases resilience and directness at the cost of link expense and routing complexity. Hub and spoke simplifies management and supports centralized inspection, but can introduce hairpin latency and hub dependency, while point-to-point is direct for dedicated links, but does not scale well as connectivity needs grow. You avoid pitfalls like hidden single points of failure at the hub and overmeshing that creates inconsistent policies and operational drag. You improve any topology by standardizing routing, documenting expected paths, and testing failover so resilience is real rather than assumed. Assign yourself one topology comparison drill by taking a single scenario you encounter this week and choosing 2 candidate topologies. Then, stating aloud which traffic pattern and failure tolerance clues push you toward one and away from the other. Because that verbal justification is the best answer muscle the exam is measuring. Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.